So we've got lots of distant galaxies, we know how far they are away, we know how fast they're receding. What we find is something called the Hubble law, and it's basically very simple. It says that the further a galaxy is away, the faster it's flying away from us. Now, how are we to interpret that? I mean, you might naively say, well, does that mean we're somehow at the centre of the universe and everything's flying away? Well, no, actually. If you think a little bit more, if you think, for example, about baking bread, if you get a lump of dough and put raisins in it and stick it in the oven, then the bread expands. So all the raisins move away from every other raisin. If you were sat on one raisin, what you would see is the Hubble law, exactly the Hubble law. You'd see the ones close to you moving away more slowly, the ones further away moving away quicker, because the bread is all stretching. All of space is stretching at a constant rate. Actually, I just wanted to, I put up that little picture behind the Standard Model because that's a Geissler tube, which was the driving force behind the discoveries of X-rays and then onwards through the 20th century. It was also something called the Ruhmkorff coil, which was the way of getting high energies into vacuum tubes. And I think it is worth noting that even then, back all those years ago, it was technology, it was engineering developments that led to the advances and the discoveries in particle physics, just as it is today. It's really not changed. You look at the ILC, and it's basically that. Isn't it? It's basically a big vacuum tube with a bit of energy stuffed into it, essentially, which is what it always was then. Actually, I reminded again, I picked up a few quotes. I quite like quotes. There's a wonderful quote in the TDR, in the design report, actually, from Freeman Dyson, who says, new directions in science are launched by new tools, much more often than by new concepts. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have to be explained. Of course, you saw in the previous talk about the technological spin-offs of particle physics. Of course, X-rays, the beginnings of particle physics, tremendously useful. So, but I was thinking all the way through that talk of a quote by Feynman. He said, physics is like sex. Sure, it has some practical results, but that's not why we do it. I think this is our sun. It's a tremendous, I think, video of the sun. This is not a computer graphic, it's a real movie of the sun taken by an orbiting spacecraft that just observes the sun every day. And you see that it's a dynamic and violent place. You could fit 1 million Earths inside that ball of glowing plasma, by the way, 1 million planet Earths. It burns 600 million tons of hydrogen fuel every second into helium. So it's a powerful, gigantic object. Many years ago now, stretching back to Newton and even before, we looked at the light from the sun, and after Newton we found a way of analysing it by splitting it up into its component colours. So with a prism, essentially making a rainbow of the light from the sun, just as nature makes a rainbow of sunlight using water droplets. And this is a picture, a modern day picture of that rainbow. Now, rainbows, of course, lots of different colours from blue all the way to red, but when you look at the light from the sun in a laboratory and you're very careful and you put it through a very precise prism, then you see that it's not just an array of colours, it has dark lines in it. All these black lines crisscrossing the rainbow. What those lines are the signatures, the thumbprints, if you want, of the chemical elements themselves. See, what happens is you'll know that an element is a nucleus with electrons going around it. And each element has a different nucleus and a different arrangement of electrons. What happens with the light from stars is that the light shines through elements in the star's atmosphere, to elements like hydrogen and oxygen and helium. And because those elements have different structures of electrons around their nucleus, they absorb different colours of light, very specific colours that correspond to moving the electrons around in very specific ways. So, for example, these two lines here are very famous. They're called the sodium lines. Sodium absorbs light in the yellow part of the spectrum. If you heat sodium up, it emits light in the yellow part of the spectrum. Why? Because of the way its electrons are arranged around the atom. So what you're seeing here is the signature, the fingerprints of elements in the sun. That's interesting in itself because you can immediately read off what the sun's made of, because you can do an experiment on Earth, see which colours the elements absorb or emit, and you can look in the starlight. You can see what the stars are made of. But also, and this is the point for looking at the wider universe, something very interesting happens when you look at these spectrum, these black lines in the rainbows of the most distant stars and galaxies. So here's a distant galaxy. You can look at the light from that galaxy. What you find, of course, is that the spectrum is the same. The black lines are all the same because chemical elements are the same across the universe, except that in all distant galaxies, the lines are shifted. They're moved. They're not in exactly the same place. The explanation for the shift is very simple. The universe is expanding. So if you look at a very distant galaxy, then you find all the distant galaxies are rushing away from us. Think about what that does to the light. What happens to the light is the light begins its journey from the distant galaxy. Light is a wave. You just imagine a wave on its journey through space. The space is stretching because the universe is expanding as the light journeys from the distant galaxies to us. What does that do? Well, it stretches the light. So the wavelength of the light is stretched. The wavelength is the colour. Red light has got a bigger wavelength than blue light. So as the light, let's say it comes from a star, it's a hydrogen, let's say, emits a line up here, and that journeys across the universe to us, it gets, actually, let's start in the blue. So let's say there's an element down here that emits light in blue. It journeys across the universe, it stretches, it stretches, it stretches. It moves towards the red bit of the spectrum because it gets stretched. And so you see the whole fingerprint of the atoms moved from the blue bit of the spectrum to the red as the light gets stretched, as space stretches. That's what we observe. So that's a very direct measurement that tells us that the universe is expanding. Here's Albert Einstein. Einstein was a genius because he thought very simply, often in pictures, about how the world works. And what fascinated him back in the early 20th century, so 1905 or so, was a result from a Scottish physicist called James Clerk Maxwell, who predicted, although he didn't know it really at the time, but he predicted that light travels at the same speed no matter how you look at it. It's a very odd thing to predict, but that came out of the theoretical physics of the 19th century from experiments on electricity and magnetism. Einstein was the first person to take that genuinely seriously and say, what does it imply? What happens if I say nature does work like that? So no matter how I move relative to you, we all agree on the speed of light. Well, he came up with a beautiful so-called thought experiment to work that out, and I can tell you that in about a minute, and it's the heart of relativity. He thought of this thing called a light clock. So imagine that I've got a very strange kind of clock, which is just two mirrors sat there like that. And my pendulum is light bouncing between the mirrors. So we can imagine 1 tick, 2 ticks, 1 second, 2 seconds, 3 seconds. It works as a very accurate clock. But remember that we've agreed that we all agree on what the speed of light is, no matter how anyone moves around. So what happens if I get this clock, literally on this stage, and I just walk along the stage? What do you see? Right? You see the clock ticking, but because I'm moving, you see something that looks more like that, because I started off over there and I walked over here, so the light, from your perspective, bounced along like that in a triangle. What does that imply? Well, if it's really true that we both agree on the speed of light, we both think it's the same, then you see my clock run slower than I do. Why? Because the light had to travel further to make 1 tick than it did when it was standing still. So that's a prediction. It's a very strange prediction. It says that moving clocks run slow. Time slows down when you move, from your perspective, watching me move along the stage. That turns out to be right. It turns out to be true. And in fact, the factor by which it slows down, which is given by this little equation here, you can work out using Pythagoras. And the reason I show the equation is because you might just be able to see, if you know the square of the hypotenuse is equal to the sum of the squares of the other two sides, you know that. You might just be able to see that, the squares and the square roots and things in here. When you just work it out, that's the answer you get. That's fascinating because that equation is built into the satellite navigation system. So when you get into your car and you set a satellite navigation and off you go, then the satellite navigation system works basically by measuring time differences between clocks on satellites and clocks on the ground. The satellites are moving relative to the ground and they're high up, so gravity is a bit weaker. Turns out that that means time passes at a different rate. How much? Well, Einstein predicted 100 years ago that it would shift by 36,000 nanoseconds per day. A nanosecond is 1,000 millionth of a second. That doesn't sound like very much, 36,000 nanoseconds. But light travels 30 centimeters in a nanosecond. So that means that the satellite navigation system would drift by 36,000 lots of 30 centimeters in its position measurement. It's about 10 kilometers. So the satellite navigation position would change by 10 kilometers a day if you didn't take account of that, which Einstein works out in 1905 by thinking about a light clock with two mirrors. Beautiful bit of physics, and it found its application a century later in satellite navigation. What's that got to do with gravity and these measurements? Well, Einstein went on from thinking about moving clocks to thinking about what happens to time and space in the presence of heavy things like planets and stars. And he found, or his theoretical prediction was, that not only does movement bend space and time, but heavy things like planets and stars bend space and time as well. And he made predictions about what that means. It actually means that when you're traveling through space near a planet, you feel like you feel a force because you're moving through bent and curved space and time. That force is gravity. It's a beautifully elegant theory. In fact, I even wrote that down. That's Einstein's theory of general relativity. The whole theory of gravity, the best theory of gravity we have in one line. Actually, this thing here just tells you how the mass of a planet or a star is distributed, and this thing here tells you how space and time curve. That's it. That's all there is to it. And then the picture is that as things move through this curved space, they bend because they're going through a curved space, and that's what we feel as the force of gravity.
Astrologers. What's your term for them?
Do you know we've got?
Do you know how I'm letting you say that if you want?
We got in all sorts of trouble for this. It was Dara O'Brien's fault.
It's all Dara
primarily
on
stargazing. But I did have a history with them.
Matter.
No, I didn't. But the thing is, I mean, I was quite surprised that there's kind of quite a vocal community of them that are really serious about it. You know, I just thought, well, it's just people like, you know, writing horoscopes in papers, but they really seem to get quite upset about it. Yeah. See, there are two ways you can see pseudoscience. And it depends on which particular pseudoscience. One is that it's a bit of harmless fun, and that's what I always kind of, astrology is like harmless fun. But actually then you can get, let's say, when you go into the medical arena, and my friends, you know, Ben Goldacre and Simon Singh particularly fight against this a lot.
Absolutely.
And of course Simon got sued for he didn't get sued for saying that it was a particular story about chiropractors curing childhood ear infections by spinal manipulation, right, which is a very odd thing to sort of claim. But he got into a hell of a mess and got sued.
Well,
it almost cost a lot of money.
This whole sort of libel action, changing of libel laws.
Well, the libel law may well get changed,
yeah.
partly as a result of that case. So then you go into dangerous territory. So the thing is, how do you, what are you to do as a scientist, right? Are you to say, well, that's harmless, so we'll leave it alone? But of course, those things, I mean, when it turns, you know, for example, I mean, the extreme is, for example, homeopathic malaria treatment.
That's
right. So people have taken
instead of
homeopathic malaria pills, right? So essentially drink water and then go to Zambia or something, which is one of the, and you get malaria, which is because you do, because it doesn't work, right? But I mean, it doesn't work. It's like drinking this and saying that'll protect me from malaria. It won't, right? It's not. But so at some point it ceases to be harmless. And so my view in general is that it needs to be challenged at all levels. There's no silly kind of argument like a thin end of the wedge or something. It's not that. It's just that if you believe that rational thinking and reason is the way to run a country, which is that's a kind of almost controversial thing to say, I think government policy should be based on reason. You know, and they're
Really?
like, what's that?
I think that's a bit extreme.
It's ridiculous. Yeah, steady on. Then I think that you have to actually say that these things are essentially not don't exist in the domain of reason. Should we put it that way?